lately, a lot of my interest has been dealing with the floor function, or the greatest integer function, the function that maps the argument to the greatest integer less than the argument. So what we're dealing with tonight is actually a limit. It's a right-handed limit of an exponential function that has the floor of the reciprocal function as its exponent. So it sounds hard, but I've come up with a lemma for you all that makes this thing melt in your mouth. This lemma states that the floor of the reciprocal function is equal to k if and only if x is actually trapped in this interval open 1 over k plus 1, closed 1 over k. Now notice I did exclude two pretty obvious exceptions here. I had to set theoretically subtract 0 and -1 from the integers here, because if you put 0 in for k, this would be undefined here, and then also -1, you would have an undefined division by 0 fraction right there. So, but in any event, it's pretty easy to believe because, for example, 1 over k, if you take 1 over k and substitute it in here, 1 over k is k, so that takes care of business. But you couldn't substitute 1 over k plus 1 in because you would get 1 over k plus 1, and we're looking for a floor of k. Now, just in case you don't believe this, let's work a special case here. Let me see if I can get to trying to annotate here. Now, let's go ahead right here and pick k equal to, let's say, 2. All right. Now, so in other words, that would go in two places. We'd go right here. This would be the k floor level you were looking at for 1 over x. Now, but over here, that says that would only happen if x were in this set, and I'll leave out the x part. It's understood. 1 over k plus 1 over, that would be 1 over 3, right? Okay, and then open, and then 1/2 closed, like that. Now let's take a look at this and just make sure it makes sense. Let's pick a number in this set. This isn't too bad. 1/3 is the same as 2 over 6, right? And so what 1/2 is the same as 3 over 6? Yeah. Okay. So what would a number be between those two? Okay, if you added those up and divided by 2, wouldn't you get 5 over 12? Okay, I'm leaving out a little bit of the arithmetic, but if you this would be what 2 plus 3 is 5 over 6, and then divide by 2 and you get 5 over 12, right? So 5 over 12 is definitely contained in this interval, because this would be 4 over 12, so 5 over 12 would just be right in the middle, right? But take a look at what happens when you substitute 5 over 12 right here. You would get 1 over 5 over 12 floor, right? 1 over 5 over 12. And again, that would be contained within the floor function. It's the argument to the floor function. But you see, that's equal to the floor of just the reciprocal of 12 over 5, right? All right, well, the floor of 2 and 2/5 has to be 2, right? That's what the floor function does. It chops it off, takes it down to the next integer, okay? So just again, some of you may have known that, but if you haven't seen this notation before, that's why this whole thing works. Now, the reason why we're looking at this is because let me clear this out here. Clear. Okay. All right. Now, the reason why this is of interest is we are trying to evaluate a limit that involves the floor of the reciprocal function. Okay. So keep this thing in mind as we move along. We may have to come back to it. Okay. Now, what I did right here, because we are approaching -1/4 from the right, so we need an interval that contains those sort of values. So numbers to the right of -1/4 are contained in this interval, but according to that lemma, this would correspond to a -5 for the floor value. You see how the lemma just does everything for us? Now, if that doesn't make sense, again, you're kind of guided by the fact we're doing a right-handed limit here, right? A right-handed limit. And so we need for the values to be to the right of -1/4, and that happens precisely on this interval. In other intervals, but it happens on this interval. But this interval happens to be lucky for us because it corresponds to a floor value of -5. So, and again, I don't like doing this, but just to make sure you know, I was just using this in reverse. Started right here, then went to K, all right? So in other words, I started with the interval, then went back to the floor level. Okay, now let's get back to the problem. Now, but basically that you're done with the problem right now. So therefore the limit is x approaches -4 from the right. Now I did this just brazenly, you know how in calculus you can put the limit inside the limit as long as both functions are continuous. Well, I'm gonna go ahead and make the assumption all those conditions are met, but it does work out very nicely here. And y'all, what I did is I just simply substituted -5 in, because I mean that's what the floor of it. That's what the floor of this is in this particular interval, and that gives us the right-handed limit of 1/243. Okay, 1/243, pretty small number. Now, I don't want to stop right now. I do want to talk about one more thing. I want to show you we've done a little bit more than just compute a right-handed limit. We've also shown, and some of you I guess already see it, we've already shown this function can't be continuous at -1/4. And you all remember let's see if I can get this to happen again. Boys, there we go. Okay, you'll remember this limit, the limit definition of continuity from calculus, and I've always seen it stated like this: the limit is x approaches a. Okay, that's supposed to be as x approaches a. That's supposed to be a little arrow right there, folks. A little arrow. Okay, of f of x, and this always stumped kids on the test. They just didn't understand, the notation was too much for them. They would put f of a right here, for example. But this literally is a power-packed limit definition for continuity. All right, a function is continuous if and only if this holds for all values of a. All right, and you think of it as a pointwise definition of continuity if you want, right? So that says the limit as x approaches a of f of x is equal to f of a. But notice what happens when you do exactly that here. If your f of x is this entire thing right here, you would get 3 raised to the floor of -1/4. Excuse me. Oh, I'll put 1 over. I'm getting a little 1 over -1/4. Hopefully that's still legible to you guys, all right? But notice, folks, that that would just be, since the floor, that would be the floor of -4, but the floor of any natural number, any integer is the integer itself. So this would equal to 3 to the -4 here. So you see what we've done. What we've done here is shown that this function is discontinuous. We have a right-hand limit that's equal to 3 to the -5, right? And then this limit definition of continuity is being violated here because it says it would be 1/81, I guess. So anyway, hope you enjoyed that. It's not that, these things aren't that bad to work with if you can establish some computation saving limits at the very beginning of the problem. Okay.